Hi everyone, and welcome again to this video tutorial where we'll be looking at the Northwest Regional Mock Proposed Solution. This time around, we'll be looking at pure mathematics with mechanics paper 3. I doing the presentation, I'm called Data Ernest, and we are going to begin right away. So the question you are going to look at today will be a question on impulse and momentum. That is question 4 from that mock examination. Now the question reads, two spheres of equal mass traveling in opposite directions with speed ku and u, k strictly greater than 1, on a smooth horizontal floor and collide directly. Given that the coefficient of restitution between the spheres is half, and that as a result of the impact, one of the spheres is brought to rest, find the value of k. Hence, find the velocity of the other sphere in terms of u only. Find the loss in kinetic energy due to the collision in terms of m and u only. Now, in mechanics, when you are given a question, it's always good to draw a diagram where you can represent all this information very concisely. So if I draw a diagram like this one, then the spheres are represented by these circles and their masses are m1 and m2. Above, I have the values for their initial velocity, and below I have the values for their final velocity. Now, in order to answer this problem, there are a couple of things that you need to know. The first thing you need to know is the law of conservation of linear momentum, which states that when two objects interact, the momentum before collision is always equal to the momentum after collision, provided no external force acts on them. How can we translate that mathematically? We can write it as the momentum of the first object, which is m1 multiplied by u1, we add it to the momentum of the second object, which is m2 multiplied by u2. The sum of these two momentum gives you the initial momentum of the object. Now, to obtain the final momentum, we just take their masses and we multiply by their final velocity and add them. So mathematically, this is how the law can be written. But in some cases, after the impact, some particles may stick together as one and move together. So they say the particle has coalesced. So in the case where they coalesce, then the momentum after collision will be the sum of their masses multiplied by that common velocity. So we'll be having m1 plus m2 multiplied by v, where v is a common velocity with which they move after the impact. Now, the second thing that you need to know is Newton's experimental law. And the law states that the ratio of the speed of separation to the ratio of the speed of approach is a constant. That means when two objects interact, you can find the ratio of the relative velocities of approach to that of separation. And mathematically, it can be stated as v2 take away v1 divided by u2 take away u1 is equals to negative e. In some books, you can see v2 minus v1 divided by u1 minus u2 is equals to positive e, but both of them represent the same mathematical equation. Now, with this being said, let's move on and answer the question. Now, I am going to concisely draw a diagram and represent the information from the question. So here we have the diagram. We were told that two spheres of equal mass, m, so that is why their masses are all m, and I've called the first sphere A, and the second sphere I've named it B, with speed ku and u, and they say they're moving in opposite directions. So if I consider the right direction as positive, then the left direction would be negative. So above here, I've written the speed of A as ku, and that of B should be negative ku, because A and B are moving in opposite directions. So if I had considered the left direction as positive, then this term ku will be negative and this term u will be positive. But in any case, make sure that you consider a reference and solve till the end. Now, their final velocity is what I don't know. So let me call them v1 to stand for the final velocity of the first object and v2 to stand for the final velocity of the second object or or of object B. Now, we have been told that let's find the value of K, but there's one important information from the question. We have been told that after impact, one of the spheres is brought to rest. So one of the spheres is brought to rest. We don't know. And also in the question, we have been told that K is a value which is greater than 1. So if one of the spheres is brought to rest, then either VA is 0 or VB is 0. That means either the final velocity of A is 0 or that of B is 0, but not both of them. So we need to find the values of VA and VB. By doing what? By making use of those two equations that we saw above. So from the law of conservation of linear momentum, the momentum before impact will be m multiplied by ku. I add it to m multiplied by negative u is equal to the momentum of the spheres after impact, which is mva. I add it to m times vb. So notice that m is common to each term, so I can cancel out m from each of these terms. So I'll be having VA plus VB is equal to KU, take away U. Let me call that equation 1. Let me also use the idea of Newton's experimental law, and I'll have that from Newton's experimental law, their speed of separation, which is VB minus VA, divided by their speed of approach, which is negative U minus KU, is equals to negative E, and E was given as half. Now, I can just multiply both sides by this denominator so that it cancels out and move on to the right-hand side of the equation. And so I'll be having VB minus VA is equals to negative half into negative U minus KU. Now, negative multiplies each of these terms and gives me a positive term. So I'll now be having VB minus VA is equals to positive U on 2. I add that to positive KU on 2. So let me call this equation 2. What I'm left to do is to solve this equation 1 and equation 2 simultaneously. So let me write down the two equations so that I can solve them simultaneously. Now, notice that I'm looking for VA and VB so that at the end I can see which of them is 0. So if I add equation 1 with equation 2, the terms in VA will vanish because of course they have the same coefficients but different signs. So VA vanishes. Then I'll be having 2VB is equal to, I just add the right hand side, which is KU minus U. I add U on 2 plus KU divided by 2. Let me just bring like terms together. These are terms in KU. So the coefficient of this term is 1 and that of this term is half. And 1 plus half gives 3 divided by 2. Then in the same way, the coefficient of U here is negative 1 and that of U is half, and negative 1 plus half gives us negative half. So this is what I have. The two terms share the same denominator. I can maintain that 2VB is equals to 3KU minus U divided by 2. And I can now divide both sides by 2, or I multiply each term by half. The 2 multiplies 2 and gives me 4. So VB is 3KU minus U divided by 4. Of course, I can factor out U from these two terms, and I have VB is U into 3K minus 1 divided by 4. So this is the final velocity of B. Then, if I go back to equation 1, I can make A the subject of VA the subject in equation 1, and VA will be equal to KU minus U. Then I send VB the other way, and I have minus VB. So I know the value of VB. Let me just substitute and simplify everything to obtain VA. When I substitute, I have this. Remember, this negative sign would distribute amongst all the terms in this numerator. So when it distributes, this term become negative and this other term become positive. So I'll just find the LCM and distribute the terms. Then I'll be having 4KU minus 3KU gives me just KU, and negative 4U, 3U divided by 4. So this is the value of VA. So VA now will be U into K minus 3 divided by 4. So I've had the value of VA and VB. Remember, in the question, we were told that one of the spheres is brought to rest as a result of the impact. So if I suppose that VB is brought to rest, that means its final velocity should be 0. And in the case where VA is brought to rest, its final velocity too is 0. So I will just equate both VB and VA to 0 and solve for the value of K. When I'm solving for K, I'll go back to the premises in the question where I was told that K is a value greater than 1. Now, this is the value of the final velocity of object A and final velocity of object B. Now, let's suppose that VA is 0. So I will take this term and equate to 0. Then u divided by 4, I can divide both sides by u over 4, it vanishes. So K minus 3 is equals to 0. So I send negative 3 the other way, K is equals to 3. And 3 is a value which is greater than 1. So indeed, the final velocity of A is 0. So A is a sphere that is brought to rest because the value of K satisfies the premises that was given in the question. But let us try for VB and see. Now, let's suppose that VB is equals to 0. That means we'll take this and equate to 0 and solve. We do the same thing, we divide both sides by u on 4. So I have 3k minus 1 is equals to 0, and k will give me 1/3. And 1/3, of course, is less than 1. So it means the final velocity of B is not 0. So B is not brought to rest. Now, the next part of the question was that let us find now this velocity of the other object in terms of u only. We have had the value of k as 3, and we know that VA is 0. So the velocity of the other sphere will be the velocity of VB. So I just come here and I replace k with 3. So I'll be left with 3 into 3 minus 1. And 3 times 3 gives us 9, minus 1 gives 8. 4 goes into 8 2 times. And the velocity of B will be 2u meters per second. So I have the velocity of B. So I can now I can come back to the same figure and I write out their velocities. So instead of writing Ku, I will replace K by its value. Then I go to the final velocities, and A has been brought to rest, so its final velocity is 0, and B is moving with a velocity of 2u after collision. So I can go ahead and solve the other question that will be asked. Now, the other question was that let us find the loss in kinetic energy. We know that when two objects interact, energy is lost, maybe as heat, sound, or energy of deformation. Now, Ke loss is given by the kinetic energy the system had before collision, take away the kinetic energy the system had after collision. So that means Ke before will be Ke of the object A. I add it to Ke of the object B, and that is before. So what is kinetic energy? Half of the mass multiplied by the velocity, all that squared. That's why I have half m into 3u, all that squared, then plus half m into negative u, all that squared. So this will give me the kinetic energy the two objects had before impact. So doing the maths, I can factor out half m into plus u squared, 9u squared plus u squared give us 10u squared, and 2 goes into 10 5 times. So simplifying everything here gives us 5mu squared. So this is the kinetic energy of the body before collision. Now what about after? After will just be the Ke that each of the object have, but after impact. So I just find the kinetic energy of each of the particles, but of course the kinetic energy of the sphere A after impact is 0, because after impact is brought to rest and it is not moving, so it has no velocity. Now, so the only kinetic energy after impact will be the Ke of the sphere B. So we just find the kinetic energy of sphere B, which is half m into 2u all that squared, which give us half m into 4u squared. 2 goes into 4 2 times, which gives us 2mu squared. What I'm left to do is just to fit this into this formula, and the kinetic energy lost will be equals to the Ke before, which is 5 mu squared, take away Ke after, which is 2 mu squared. So Ke loss is 3 mu squared joules of energy. So we have come to the end of this presentation. So if you do have a question or you have a doubt, then please just place that in the comment section below. And if you have some recommendations of future videos, you can as well put them in the comment section, and when I have the time, I may decide to make a video particularly for you. So thank you so much for watching, and stay tuned for more videos. Thank you.